Hello, and let's talk about Schrodinger's equation and the quantum description of the atom. Now, the Schrodinger that we're talking about is actually the same Schrodinger that's very famous for his cat. And what it says is if you have a classical theory says if you have a proton, if you have a nucleus here, then you'll have an electron, and the electron is in a very discrete position. But what actual Schrodinger's equation says is actually, it's like a standing wave, and it gets smeared out all around the atom. So instead of, so we can't say exactly where that electron is. What we can say is we can assign a probability of it where it is. So if we were to do this, Schrodinger's equation, this is just in the x dimension. So if we were to take our electron, and I'm sorry, let's get rid of that. If we were to take our electron and look where it is on the x dimension, what's the probability that it is exactly there? So P is the probability, and that's going to be between 0 to 1, equals psi, and this is going to, we're going to take the absolute of this. This is the wave amplitude function. This is wave function, or Schrodinger's wave function, amplitude function. And we're going to square that, and we're going to multiply it by the size of the position. And that basically tells us our position, or x dimension, that tells us what the probability is of the electron being between this point and this point. And usually we work out a 95% probability. So if we've got the atom there, we can say that the electron is somewhere in a cloud in there with a 95% probability. It could also be out here or up here. It could be in orbit around Alpha Centauri. But so that's what that tells us. The trouble is this wave amplitude function here. This is meters. This is probability. Probability does not actually have an amount, have the unit, so it's going to be between 0 to 1. Okay, so what that tells us is, yeah, how likely something is to be anywhere. But due to quantum mechanics, we cannot precisely say where it is, and therefore we cannot give 100. We can't say it's definitely there, so it's definitely going to love that. What we can say is there's a probability of that there, and therefore there's a probability of this event occurring. And if that's saying hit your brain, yep, welcome to quantum. Now, what we can say is if we're looking at an atom, so say we've got a nucleus of some description here, we're going to have some electrons around this atom, and they're going to be in their little clouds. And what's going to happen due to the way nature is, they're going to be trying to rest at their lowest energy level, the lowest thing. And so they're trying to all be sitting down here. But according to Pauli's exclusion principle, you can't have two objects in the same place at the same time. And we'll extend that a bit further. So what we actually do is when we're working these out, we actually assign these. Basically, we've got 4 quantum numbers that we apply to anything. So we've got n, and that's our principal number. And this number can have a value of 1, 2, 3, 4, and we call this the shell. This is going to be the shell number. Then what we've got is we've got L. This is our angular momentum. And this can have a value of 0, 1, 2, any value up to n, up to this number, -1. So for the first level, for when n is equal to 1, the maximum value can n minus 1 is going to be 0. For n is equal to 2, then this can take in values of 0 and 1, because n2 minus 1 is 1. So for 3, the maximum value is going to be 3 minus 1, which is 2. So angular momentum can be 0, 1, 2. But we're going to start with the lowest energy state, which is the 0, go to 1, then to 2. We also have ML, which is our magnetic quantum number. And this one can have values of 0, plus or minus 1, plus or minus 2, dot, 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 up to the same number as L. So this can have any value. So when it is equal to 1, L is equal to 0, and that's a M1, or ML, that's an L, can only be 0. When n is equal to 2, this number can be 1, 0, or 1. And when L is 1, this number can be minus 1, 0, or positive 1. We're going to start with the lowest number, we'll work our way through. When n is equal to 3, L can be 0, 1, 2. So this can be 0, 0, plus or minus 1, plus or minus 2. And the other thing that we've got is we've got MS, and this is spin. And it's not something we're talking about in the political sense. This can have a value of plus or minus 1/2. So let's actually apply this. So if we take a atom, for example, if we have let's take the lithium, this is going to be the example in example 9.3 or exercise 9.3. Lithium has got 3 electrons, so they can be in 3 states. So we can go n is equal to 1. So that means L is going to equal 0, because it can only equal 0. ML equals 0, because this number cannot be bigger than that number. And spin, actually let's do helium. Spin MS can be, it's going to be plus 1/2 the first time round. And then we stick a second one in, because these, according to Pauli's or Pauli's exclusion principle, an atom cannot have 2 electrons with exactly the same set of numbers. So if this is 1, 0, 0, positive 1/2, we cannot have another electron in state 1, 0, 0, positive 1/2. So we're going to have negative 1/2. So this number here, okay, so let's try that. So let's try and actually apply this to a more complex, let's go all the way up to helium. So we're going to have our atom, our type. We're going to have number of electrons. And let's put a line down here. Then we're going to have our number, the shell number. L, this is actually often called a subshell. So when L equals 0, we call that's going to be subshell S. When L equals 1, that's going to be P. When L equals 2, that's D. And when L equals 3, that's F. And that's, yeah. And so on. We can go higher than that. But okay, so let's try this. So when we're packing it on here, okay, what else have we got? We've got ML and we've got MS. So let's start off with hydrogen. Hydrogen's got 1 electron. So we're going to choose the lowest number we can. So remember, N is equal to 1, 2, 3, dot, dot, dot. So we're going to stick in the lowest number value there we can. So that's going to be 1. L is equal to 0, 1, 2, N minus 1. So the lowest value that's free for L is going to be 0. ML, remember, is going to equal 0 plus minus 1 plus minus 2 dot 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 up to go. And the lowest value we can stick in there is going to be, well, only value we can stick in there is going to be 0, and then spin ms equals plus minus half. So to destroy this system, we're going to put in plus half. So next atom we have is helium, and helium has 2 electrons. So this shell is not full because we've only put 1 spin state in. So you're going to go, what is it, 1? This is still only able, these two are still only able to be 0. Minus half. And now when n is equal to 1, we have no other options. I can't actually draw any other combination of 4 numbers obeying these rules that I have not done before. So what we do is next we go into lithium. So lithium is going to have the same setup. It's going to have these 2 electrons. So if we look at lithium molecule, we're going to have these 2 s orbitals. These are, we call this 1s because n is equal to 1 and L is equal to 0. And when L is equal to 0, we say it's going to be S. So these are going to be 1s electrons. So all the 1s, 1 level electrons. So we're going to start to 2. Now, 2, I can either have L is equal to n, because n equals 1, I can have L is equal to 0, or I can have L is equal to 1. I'm going to start with the lowest possible energy state. So the lowest number of L I can have is 0, and that's going to be plus half. Because again, when L is equal to 0, then this can only be equal to 0. Let's go choose the next one, lithium. What's after lithium? Beryllium. Or, well, we've only done 1 of the 2 spin states, so we can go 2, 2, 2, minus half. So these 2 here, these are 1s orbitals. We call this 2s because second shell, this value is equal to 0. Okay, after that we go on to boron. Boron's going to have 5. Okay, so we've done both of these, but we can also have L is equal to 1. So we can go to L is equal to 1. And then we're going to go, what's the lowest value we can have for here? Well, we can have positive 1, 0, or negative 1, because remember, because this is 1, we can go right up to here. So the lowest possible value of this can be is negative 1 plus half. And then we're going to go into carbon, which is 6, and we're going to keep going through this number here. And when we run out of these numbers, then we're going to tweak the spins. Okay, so carbon's going to have these 5 electrons. So this is a, well, because L is equal to 1, these are going to be 2p electrons. So this is going to be 2, 1. The next value ml can have is 0, half. Then we get to nitrogen, 7. So it's going to be 2, 1. Next value that ml can have is 1. Again, spin is positive half. Then we get to oxygen. Now we've run through all the possible options that this can have, but we haven't run through all the options the spin can have. So this is going to be 2, 1, negative 1. Let's make sure we don't avoid Pauli. It's going to be negative a half. 9 is going to be fluorine, which is highly reactive, 9. So 2, 1, well, negative 1, next one up is 0, negative half. And the last one in this series is going to be neon, which is going to be 10, which is 2, 1, positive 1, negative half. And that fills up the 2p shell. That's all the possibilities we can have where n is equal to 2 and L is equal to 1. So okay, so when we're filling shells, it doesn't actually go in a very, well, they're always trying to fill up the lowest possible energy states. And the way that shells work is they fill up 1s. So what's that? This is going to be NL. So we fill up the 1, 0, Then we fill up the 2s, which is going to be 20. Then we fill up the 2p, it's going to be 21. Then we fill up the 3s, so far this seems reasonable. 3s, which is going to be 31. Then we're going to throw up the 3p, which is going to be 32. But this is where it gets strange, because if we was just literally running these in sequence, the next one should be 3d. But in actual fact, this will actually fill up the 4s shell before it fills up the 3d shell. Okay, and then we fill up the 4p, that's 42. Then again, before we get on to the 4d, we start filling up the 5s shell. So, and then we fill up the 4d. And there is a map of all of this, so you can actually find this easy enough online. Oops, I can't draw a straight line down with this equipment. So when we're filling up the shells, they actually follow this strange manner, which we're not going to get anywhere near this high in a physics test or an exam. But the chemists, yeah, this is your life. So, yeah. So anyway, when we're doing this, the thing about this, so this is Bohr's atom and quantum, Schrodinger's atom thing. So this is quantum atom. And this explained very well why the periodic table does what it does. And so therefore everybody's happy with it. Okay, so I will catch you next lecture, which will be on lasers.